Hi students, good morning to one and all. Today we are discussing our last topic of the fourth unit, that is nothing but none other than computing the transitive closure. Okay, what is the meaning of the what is the meaning computing the transitive closure? What's that main aim of our concept in the sense? Let us see computing the transitive closure of a graph. Let us explain now. Look at the graph, all of you here, the PDF document here. Okay, the PDF document here. See, look at all of you. All of you take the notes and then write the graph. Okay, computing the transitive closure of a graph. Here the graph in the sense, we know all of you vertices and edges, G of V comma E. Here we look at this graph in the sense, directions. Graph is nothing but it is a directed graph. It is a way of directed graph. Here one of the reachability matrix, we want to represent it in a cost adjacency matrix. Cost adjacency matrix లాగా మనం రిప్రజెంట్ చేసుకోవాలి. ఇక్కడ ఎన్ని ఎలిమెంట్స్ ఉన్నాయి, ఎన్ని నెంబర్ ఆఫ్ ఎలిమెంట్స్ హియర్ వీ హ్యావ్ ఇన్ ఎ గ్రాఫ్? ఏ బి సి డి ఈ. హౌ మెనీ ఎలిమెంట్స్ వీ హ్యావ్? 5 elements. Okay, let us take, we have to take some cost adjacency matrix. Left row side and column side we have to write A B C D E, and column side A B C D E. First of all, we have to take the diagonal elements A to A, B to B, C to C, D to D, E to E are all are ones. Okay, and now we have to see the A to B direction is there or not, it is a directed or not. Let us check. A to B is a path is there, that's why we have to write 1. And coming, let us check. A to C is A to C, the way is there. See, look at this A to C. How the A to C way? A to D and D to C. The directed path is there. That's why we have to rotate A to C is 1. Coming to the A to D, direct path, it represents the arrow. Look at the diagram. A to D, directed way, we have to represent it an arrow. That's why A to D is as 1. And coming to the A to E, yes, A to D, one arrow will be there, and D to E, another arrow will be there, and there is a path between A to E. That's why we have to rotate 1. Up to now we have to understand. And coming to the B, B to A, is there path? No. That's why we have to rotate 0. And coming to the B to B, we know all diagonal elements must and should be 1. Okay. And B to C, is there path? B to C? No. There is the reverse direction, is there arrow? No. Nothing but 0. B to D, is there? No. Is there no path? That's why we have to write 0. And B to E, is there path? No. 0. And coming to the C, C to A, is there path? C to A, is there path? No. Cancel. And no, that's why we have to write 0. C to B, is there? C to B, yes, C to B is the direction is there, that's why we have to write it 1. C to C, 1. C to D, is there? C to D, no, that's why we have to write 0. C to E, is there? No, reverse direction is there, that's why we have to place it 0. And coming to the next D, D to A, is there way? No, directed way is not there, that's why we have to place it 0. D to B, is there? Look at once. D to B, D to B, yes. See, D to C, 1 arrow. C to B is there, 1 arrow. Until there is a path between D to B. That's why we have to place it 1. D to C, is there? Look at D to C, yes, 1. D to D, 1. D to E, is there arrow? We have to look at this diagram carefully, otherwise we can't able to understand the problem. D to E, is there? 1. This is the path, directed pathway representation. Okay. And coming to the E to A, E is there, E is there, and A is there. There is a path? No. That's why we have to place it 0. And coming to the E to B, check once E to B. How the E to B way? E to C and then C to B. There is a direction is there. Look at the directed graph. Okay, E to B, 1. Coming to the E to C, yes, E to C is a path. That's why we have to place it the value of 1. And coming to the E to D, is there? No. Why? Because of the reverse arrow. That's why we have to place it the value 0. And coming to the E to E, in the sense 1, E to E in the sense 1. Okay, up to now we have to understand the concept. What is that one? Reachability in the matrix representation. Okay, coming to the path relation from vertex I comma j, whatever it may be, vertex I comma j, x comma y, a comma b, whatever it may be, we have to take some path relation from vertex I comma j, or in the sense relation set we have to represent ante listen carefully, or in the sense path relation from vertex I comma j. Okay, or in the sense relation set, in relation set we have to represent what? We have to represent a comma a, in the sense ఏదైతే మనం 1 అని వేసుకున్నామో, అంటే ఏ టు ఏ 1, ఏ టు బి 1, ఆ 1 అనే వాల్యూ రిప్రజెంట్ చేస్తున్నామో అవి మాత్రమే ఈ రిలేషన్ సెట్లో, అంటే రిలేషన్ అనేది వాటికే ఉంది, ఏ వాటికి రిలేషన్ ఉందో వాటిని మాత్రమే మనం రిలేషన్ సెట్లో రాసుకోవాలి. ఓకేనా, అంటే ఏ టు ఏకి 1 అనేది రిప్రజెంట్ అయ్యిందిగా, వే అనేది డైరెక్టెడ్ గ్రాఫ్ అనేది ఉంది కాబట్టి వీ హ్యావ్ టు ప్లేస్ ఇట్ ఏ కామా ఏ, అండ్ దెన్ ఏ కామా బి, ఏ కామా సి, అండ్ దెన్ ఏ కామా డి, అండ్ దెన్ ఏ కామా ఈ, అండ్ కమింగ్ టు ద నెక్స్ట్ బి కామా బి, సి కామా బి, అండ్ దెన్ సి కామా సి, and then D comma B, D comma C, D comma D, D comma E, and then finally E comma B, E comma C, E comma E. These are the path relation from vertex I comma J. Here we have to, here what is this computing trans to closure of a, what we have to computing the trans to closure of a graph. Let us discuss the theory part now. Okay, what is the computing the trans to closure of a graph G? Let us consider, let G be a directed graph. Already I shown, let G be a directed graph whose adjacency matrix is A. Whatever matrix we have to take, that matrix is representation as A, B, whatever letter. Okay, the reflexive trans to closure of G denoted by A asterisk. What is the reflexive trans to closure of G? It's denoted by the letter A asterisk. Okay, is a matrix such that A asterisk I comma J is assigned to 1. Okay, there is a directed path from node I to node J. ఇప్పుడు మనం ఫర్ ఎగ్జాంపుల్ మనం ఒక గ్రాఫ్ తీసుకున్నాం కదా, ఏ నుంచి బీకి పాత్ ఉందా లేదా, అంటే దాని పాత్ ఉందా లేదని మనం ఎలా చూసి రిప్రజెంట్ చేస్తున్నాం? వీ హ్యావ్ సీన్ దెర్ ఈస్ అ డైరెక్టెడ్ పాత్ ఫ్రమ్ నోడ్ ఐ టు నోడ్ జే ఇన్ గ్రాఫ్ జీ. ద ట్రాన్స్ టు క్లోజర్ ఇట్ క్యాన్ బి కంప్యూటెడ్. వాట్ వీ హ్యావ్ టు కంప్యూట్ హియర్? reflexive trans to closure of G, it denoted by A asterisk. Okay, that is assigned to identity matrix plus A square plus and so on up to plus A power n minus 1. What is the reflexive trans to closure of G? It's denoted by the letter A asterisk. We want to calculate. Now we have to prove that I in the sense identity matrix, it is represented as 1 0 0 0 1 0 0 0 1. This is nothing but identity matrix plus A in the sense whatever 3 by 3 matrix we have to take, plus A square in the sense whatever 3 by 3 matrix we have to take in, plus and so on up to how much? A power n minus 1, A power n minus 1. Okay, this is the computing the trans to closure matrix is A. The reflexive trans to closure of G, it's denoted by A asterisk. It is a matrix that such that we have to represent A asterisk I comma J is assigned to 1. There is a directed path from node I to node J in graph G. The trans to closure it can be computed as A asterisk is assigned to I plus A square plus and so on up to plus A power n minus 1. Next video we have to discuss in next video we have to discuss the theorem what the theorem represents. Here one of the analysis we have to look at this analysis here. Look at the analysis here, all of you look at the analysis. What is the time complexity of trans to closure is big O of order of n cube. What the time analysis, the time complexity of trans to closure is order of n cube. Here we have to use one algorithm that is nothing but Warshall algorithm. What algorithm? Floyd-Warshall algorithm. Okay, here we use one more algorithm also, that is nothing but a depth first search algorithm. Do we have to use depth first algorithm? We have to reduce the time complexity in this problem. Okay, what I want to say, once again I repeat, what is the analysis of trans 2 closure, trans to computing the trans 2 closure analysis? The time complexity of trans 2 closure is order of n cube. Okay, here we have to use, here now we have to observe. So here we have to observe Floyd-Warshall algorithm and DFS algorithm. We use DFS algorithm here, reduce the time complexity. How the condition will be, in the sense, for I is equal to 0 to n condition. Okay, we have to check condition in the flower base depth first open. Here I have to write the condition here, right side we have to look at this in this PDF. For I is equal to 0 to n, open the flower base and depth first search. For each and every vertex we have to do the depth first search. At that time we have to reduce the time complexity in that problem. Okay, what are the analysis? Time complexity of trans 2 closure of a graph G is order of n cube. Here we have to use two algorithms, that is Floyd-Warshall algorithm, and one more we have to use here, depth first search algorithm. In the depth first search algorithm we use here we use depth first search algorithm. We want to reduce the time complexity in that given problem. What are the given problem they given? We have to reduce the time complexity. Okay, up to now we have to understand the what is the computing the trans 2 closure of a graph G. Next video, further video, we have seen the theorem and statement. What are the theorem we have to use in computing the trans 2 closure of a graph G? Okay, thank you.